Now we are moving into the second type. In the second type, this is a reducible Markov chain, but here each close communicating class consists of only one element, that is nothing but the absorbing states, but more than one close communicating class are possible. Therefore, this type is called with one or more absorbing states. Here also my interest is to find out the stationary distribution. The stationary distribution, here the interests are of the different way. One is the probability of absorption, the other one is what is the mean time before absorption. So, for that I am making a further assumption, the state space is going to be finite. Okay. So, with that I am making a canonical form. The canonical form consists of all the absorbing states that I label it as a capital A and all the transient states as a capital T. Therefore, the state space S is a union capital T. Therefore, the canonical form, I collect all the absorbing states in the first few rows and then remaining will be all the transient states. Since the absorbing states P I I is equal to 1, therefore, you will have a identity matrix for the submatrix of the matrix P corresponding to A to A, whereas A to T absorbing states to the transient states, that elements are going to be 0. So, that is a submatrix with the entities 0, whereas a T to A will be submatrix capital R and a T to T will be submatrix Q. So, if you go for what is the n step transition probability, since it is identity matrix, again also you will have identity matrix, whereas a T to A, that is going to be a function of n, whereas a T to T will be a power n, that is q raised to power n. As n tends to infinity, the system will not be in the transient states, therefore, q n will tends to 0 submatrix as n tends to infinity, and these probabilities are going to be 0 for all I comma j belonging to T. T is nothing but the set of transient states. Our interest is here what is the probability of absorption, because we have a few one or more absorbing states. So, if the system start from some transient state, what is the probability that the system will be absorbed into this absorption state? So, for that I am going to start with the Chapman-Kolmogorov equation. That is Chapman-Kolmogorov equation for the n plus 1th step, the system going from the state I to k, that probability is same as what are all the possible, the system can go make a one step from I to j and then j to k in n steps, all the possibilities j belonging to S, where S is the state space. I know either I have a either I have a transient states or all other states are absorbing states. Therefore, if k is going to be the absorbing state, then p k k is equal to 1. That means, a one step transition probability of system moving from state k to k, that is 1. Therefore, I to k in n plus 1 steps, that probability I can split, I can make I to k in one step, then forever I will be in the state k, plus I would have moved to the state I to j, where j is another transient state, it could be same also, then j to k in n steps. Now, I am defining what is the meaning of a probability of absorption, that I am denoting with the letter a suffix I comma k, that is nothing but the probability that the system starts in state I, it starts in state I, eventually get absorbed in absorbing state k. So, the first letter is the starting state and the second k is the absorbing state. So, this is the probability of absorption starting from the state I to the absorption state k. Now, I am taking the equation 1 as I make n tends to infinity in both sides. The left hand side will be a of I comma k, because as n tends to infinity. So, this will be a I k. Similarly, p j k of n, that is also a j k. Therefore, I will have a I k this side and a j. So, this is sort of recursive equation. So, this is in the element form, I can go for in the matrix form. So, I can write a I k as a matrix capital A. Therefore, in the matrix form, the previous this equation for all values of I, this equation as in the matrix form capital A is equal to R matrix, because this is p I to k, where I is the transient state and k is the absorbing state. So, transient state to the absorption state, transient state to the absorption state, that submatrix is capital R. Therefore, in the matrix form capital A is equal to R matrix plus Q matrix, that is the one step transition of system is moving from transient to transient, multiplied by A matrix. So, I can do the simplification. So, I get A matrix equal to I minus Q inverse R matrix, and here this I minus Q inverse, that is nothing but the fundamental matrix. So, once you are able to find out the fundamental matrix, multiply by the R matrix, that will give the probability of absorption starting from the transient state and reaching absorption state. And this probability is not independent of initial state, that is very important. Whereas, the previous type of reducible Markov chain, that is independent of initial state, whereas here the probability of absorption is not independent of the initial state I. So, this we can visualize through one example that I am going to present later. The next result interested in the reducible Markov chain with one or more absorbing states, that is what is the time to absorption. Basically, our interest is to get the mean time to absorption starting from the transient state to a absorbent state. That means how much time on average the system is spending in the transient states before absorption. That is very important, because many application has a reducible Markov chain in which more than one absorption states are there with the transient states. Therefore, what is the mean time up to absorption? That means how much time spending in the transient states before the absorption. So, for that I am going to define the random variable capital T I. The T I denotes the number of steps including the starting state I, in which the Markov chain remains in a transient state before entering the absorption state, absorbing state. So, there is a possibility the system would have been spending at least one step before absorption, or 2 steps or 3 steps and so on. Therefore, that is going to be a random variable. It is a discrete random variable with the possible values are 1, 2, 3 and so on. Our interest is not only finding out the distribution of T I, our interest is to find out what is the mean time up to absorption from the transient state to a absorbing state. So, this probability can be computed by find out what is the probability of T n is equal to n for some n can take the value 1, 2, 3 and so on. So, that discrete random variable probability mass function can be computed in this way. You find out what is the probability of T I is greater than or equal to n minus 1 minus what is the probability that T I is greater than or equal to n. If you find the difference, that is same as the probability mass at n. But this is same as the T I greater than or equal to n minus 1, that is same as the n minus 1th step the system is in the transient state. If Ti is going to be greater than or equal to n minus 1, that means the system spends at least n minus 1 steps in the transient states. Once it goes to the absorption state, then it cannot come back to the transient states. Therefore, the meaning of Ti greater than or equal to n minus 1, that is same as the n minus 1th step the system in the transient states. So, both the events are equivalent, therefore, the probabilities are equal. Similarly, you can argue Ti greater than or equal to n means at least n steps the system in the transient states before absorption. That is same as in the nth step the system is in the transient state. The probability of n minus 1th step the system is in the transient state, that is same as what are all the possibilities the system would have moved from the state I to j in n minus 1 steps. You add all the possibilities j belonging to t, you add all the possibilities of the transient states, that summation will give this probability. Similarly, for the x n belonging to capital T. This is in the for fixed I, where I is belonging to the transient state. Now, I will go for, I know that for I comma j belonging to T, the n step transition probability is nothing but the submatrix, that is q power n. If you recall the way we made a canonical form of a P matrix, the T to T, that is a Q matrix. Therefore, as n tends to for any nth step, that is going to be q power n. So, this is what I am using for I comma j belonging to capital T, the submatrix of p power n, that is q power n. Therefore, for I comma j belonging to T, the n step transition of system moving from I to j, that is q power n. Therefore, I can substitute here in the above equation. So, the probability mass at n, that is same as a q power n minus 1 into I minus q into E vector. Once I know the probability mass function for the discrete random variable Ti, then I can find out the mean. Mean is nothing but summation n times the probability mass at n, Ti is equal to n. If I add summation over n, that is going to be the mean time up to absorption. That is going to be, do the simple calculation, you will get I minus q inverse into E vector. This I minus q inverse is nothing but the fundamental matrix. That means, if you find out the fundamental matrix multiplied by the R submatrix, you will get the probability of absorption. If you multiply by the E vector, you will get the mean time up to the absorption.